This is Physics 102A at Porterville College, Chapter 7 homework problems. We start with number 34 with the electroencephalograms. This question gives two frequencies. The first one is 12 hertz, the second one 30 hertz, and asks what's the period. And for this, you should know that period is the reciprocal of frequency. So for the first one, we put 1 over 12 hertz, and we get a period of 0.0833 seconds. For the second one, it's 1 over 30 hertz, and that's a period of 0.0333 seconds. Number 36, the heart rate. An athlete's heart beats 145 times per minute. So there's a frequency, but we want to have it in proper units, which is in seconds and per second. So to get the frequency in per second, 145 beats per minute, multiplied by 1 minute over 60 seconds, and the minutes will divide out. So 145 divided by 60 is 2.42 beats per second, or we can say 2.42 hertz. The period is the reciprocal of 2.42, so 1 over 2.42 is a period of 0.414 seconds per beat. For number 39, we have a mass of 1.4 grams, a frequency of 1.1 hertz. We need to find the spring constant. So many ways to go about this, but here's one suggestion. We have this equation for period. Period is 2 pi over square root of, or 2 pi times square root of m over k. Frequency is the reciprocal of that. So frequency, you should get 1 over 2 pi times square root of k over m. Solve this equation for k, and you get the square of 2 pi f times mass. There are other ways to go about getting k. As I said, that's just one of them. So we get k is 0.0669 newtons per meter. Number 40, some graphing exercise. A bungee jumper undergoes simple harmonic motion with an amplitude of 5 meters, frequency of 0.125 hertz. Graph the position versus time for 2 oscillation cycles. Okay, so this is the basic formula that position x equals amplitude times cosine omega t. Amplitude is 5 meters. We have the frequency of 0.125 hertz. Let's turn that into the period. Period is the reciprocal of that of 8 seconds. When we know that, we don't have to directly plug into the basic formula. We can just do that. We have this. We have a basic cosine curve, which starts at, when x equals 0, it starts at the amplitude 5 meters. And it'll go through the cosine curve, and 1 period later, at 8 seconds, it'll have gone through the cycle again. The midpoint at 4 seconds is where it's at the bottom of the curve, so negative 5 meters. The quarter points at 2 seconds and 6 seconds are where it hits 0. So you have a basic cosine curve that goes for 8 seconds. There's 1 period. 10 seconds later, it's at 0. 12 seconds, it's at the bottom of the curve. 14 seconds, it's at 0. 16 seconds, 2 periods later, it's right back up at 5 meters again. Another way that we could do this is to use a graphing calculator, and I will show that on a second video. So we'll come back to that on the next video. Number 41, the bungee jumper. This is just showing where is the bungee jumper's position at various times. And what we should do is, let's go back up to this formula that I had for number 40. We need the formula x equals a cosine omega t. So we need a. We decided already that that's 5 meters. We need to know what omega is. So it's useful to know that omega is 2 pi times f, which is 2 pi times 0.125, or 0.25 pi. So here's the formula. X equals 5 times the cosine of 0.25 pi times t. Once you have that formula, you can plug in the various times for parts A, B, and C. Time of 0.25 seconds gives a position of 4.9 meters. 0.5 seconds gives 4.62 meters. And 1 second gives 3.54 meters. Again, when I come back in the bonus video for number 40, I can show how you use the trace function on a calculator to figure out number 41. Number 46. A mass spring system undergoes simple harmonic motion. How much time does it take the mass to go from A to 0? Useful to know, and let's think back to the cosine curve, a basic cosine function. To go from A to 0, that's 1/4 of the period. To go from A down to negative A and up to A again, that's a full period. But just to go from A to 0, that's 1/4 of the period. So for this problem, let's figure out how long a period is and then take 1/4 of that. Period is 2 pi times square root of m over k. We're given m, we're given k, so you should get a period of 0.7214 seconds. 1/4 of that then is 0.180 seconds. Number 51. Hanging a spring vertically and attaching a mass, it stretches the spring a distance of d, then pull it down, let go of it so it oscillates with a period of 1.04 seconds. What is d? We start with a force diagram. This is just with it hanging. Hooke's law says that the force pulling up on the mass is k times x. And here x is the displacement. I'll use the letter d because that's what the problem gives. So it's a force of kd pulling up. It's the weight of the mass, mg, pulling down. F equals ma. If it's not accelerating, we say F, the sum of the forces equals 0. And the sum of the forces is kd minus mg equals 0. And so from that we can get the displacement d equals mg divided by k. We'll come back to that. Let's solve for k. If period, this is what I have in the green here, if period is 2 pi times the square root of m over k, we solve for k and get k equals the square of 2 pi over t times m. Now let's plug that into the distance formula, or the displacement formula that we got right here. If displacement is mg over k, we're going to plug in this k, and we get this. Displacement is mg over m times the square of 2 pi over t. Notice that the masses divide out. We never needed to know what the mass was. And we're left with displacement as g times the square of t over 2 pi. So we get 0.268 meters. Number 68 involves a pendulum. What's the gravitational acceleration on a planet where, and there's the period and the length of the pendulum. So we're not using g equals 9.80 meters per second squared. We're on another planet here. So we take this equation for period, solve it algebraically for g. G becomes the square of 2 pi over t times the length. Plug in the values given in the problem, and you should get g is 10.54 meters per second squared. Number 69 gives a period of oscillation for a pendulum, and we need to know the length of the ropes. So we do it similarly to how we did 68, starting with the period formula, but now we're solving for length. So when you do the algebra, you get length equals the square of t over 2 pi times g. Plug in the numbers, and it gives 4.17 meters. You'll notice that mass doesn't come into the equation. So when we change the mass, there's no change in the length. or there's no change in the period. For number 71, a pendulum makes 25 oscillations in 32 seconds. Find the period and the pendulum's length. So setting it up for period is measured in seconds per cycle. So let's set it up that way. It's 32 seconds per 25 cycles. Divide 32 by 25 and we get 1.28 seconds for each cycle. That's the answer to part A. Then, for part B, we use the length equation that we got in number 69. The length is the square of t over 2 pi times g, and you should get a length of 0.407 meters. Number 77. At sea level, g varies between 9.78 and 9.83 meters per second squared. That's between the equator and the North Pole. Find the difference of the periods of a 2-meter long pendulum. So the difference of the periods is, here's the period of a pendulum at the equator minus the period of a pendulum at the North Pole. Now, really what we're looking for is the absolute value here, but I didn't want to confuse the notation by adding absolute value signs. What that means is, whether this comes out positive or negative, we want the positive answer. So, let's plug in our formulas for period. Period at the equator is 2 pi times the square root of L over G at the equator. Period at the North Pole is 2 pi times the square root of L over G at the North Pole. Now, at this point, you can plug in all the values. You know L of 2 meters, you know the two different G's. You can plug in all the values and get the answer. Or, let's take this. I'm going to do a bit more algebra with this. You can factor out of the equation. Factor out of the equation 2 pi and square root of L. So you're left with 2 pi square root of L times 1 over square root of G at the equator minus 1 over square root of G at the North Pole. And here I've chosen to plug in the values. So it's 2 pi times the square root of 2 meters times, and here are the different values. These are each 1 over the square root of the different G's. So 0.3197647 and 0.3189505. When you plug in those values, or perhaps you plugged in the values right up here, but you should get a difference of period of about 7 milliseconds, 0.0072 seconds.